Okay, so good afternoon and welcome back to the last lecture of this first day. Main lecture, of course, after this we'll have an informal discussion with the interested participants. So the last lecture is by Professor Andrey Piatnitski. He was born in Moscow. Currently, he is a full professor at the Arctic University of Norway for more than 2 decades. And also associated as a senior researcher at the Institute for Information Transmission Problems, RIS. He's a fine researcher in theory related to homogenization, and he worked on several areas of homogenization like gamma convergence and singularly perturbed differential operators, stochastic homogenization, and porous media, high contrast equations, multi-phase flows, and asymptotically thin and singular structures, boundary homogenization. Is currently also interested very much in non-local operators of convolution type. So for us, it was a toss-up between whether we give lectures on non-local operators or convolution type or stochastic homogenization. But finally, we decided that he mainly will give lectures on stochastic homogenization, but I hope maybe in the last lecture he will also spend some time on local operators, if time permits. He also guided many students. He is also a member of many editorial boards. And more importantly, he has several publications, nearly 150 to his credit, and with a large number of citations. As I said, in this course, he will be giving lectures on stochastic homogenization. And welcome, Professor Piatnitski. And now the stage is yours. Please.
Well, thank you very much for this nice introduction, and also I thank all the organizers for the kind invitation and the possibility to give this course. And I should say that it's a great pleasure after this long break related to this pandemic to see even in online mode, to see many colleagues. I'm really pleased to see this, all these participants and my colleagues. So today I will start this course on stochastic homogenization, and stochastic homogenization maybe it's too wide name, so I specify it in the subtitle, which is homogenization of operators with random coefficients. This topic, the first results in this topic were obtained by Kozlov. It's in 1979, and independently, with slightly different but quite similar approach in the works of Papanikolaou. And Varadan. It's in 1980. And then another approach based on gamma convergence, variational arguments, and subadditive theorems was suggested in the work of Dalmaso. And Modica in 1986. Well, that was just the starting point. After that, many new results, many new problems were considered in this field, in the field of stochastic homogenization and operator with random coefficients. Many approaches and methods were developed. It's impossible to mention on all of them. Later on, I will give you some list, some sketch of most important fields and results, subfields in this area. But we will study, we discussed, as was already said, we discussed with the organizer if I should explain some results which are quite recent and mostly for non-local operators. But then we decided that it's a good idea to explain first the basic ideas in stochastic homogenization and to start with classical results on operators with random coefficients, elliptic operators with random coefficients in divergence form, partial differential equations. So before I proceed with all the definitions, I would like to explain some philosophy behind homogenization and why people expected that in random case, like in periodic or quasi-periodic case, also there should be some the homogenization result should be also valid for random operators with stationary or statistically homogeneous coefficient. Let me remind that homogenization theory, the classical homogenization theory, deals with the following problem: divergence A of x over epsilon, gradient u epsilon is equal to some given function f in a bounded domain Q. Bounded Lipschitz smooth domain, it's not important at the moment. And then u epsilon, let's say we equip this problem with the homogeneous Dirichlet boundary condition. And as epsilon goes to 0, epsilon is a small positive parameter, we would like to know if we are interested in the asymptotic behavior of the solution of this problem. Of course, we should assume that the problem is uniformly elliptic to have a well-posed problem. So f will be usually function in L2 from Q. And we assume that the matrix A is uniformly bounded and uniformly coercive. So let's also assume that A of y satisfies this condition. So it's bounded and coercive. And also, for simplicity, let's assume that it is symmetric for a while. Then for each epsilon, this problem has a nice solution. It's H10 function. It's uniformly bounded in epsilon in H10. But now the question is, does it converge to something as epsilon goes to 0 or not? And it is clear that in order to have convergence to some nice limit, we should know something about this coefficient. More precisely, usually we want to know that this coefficient in a certain sense are invariant with respect to a shift or some group of shifts, some collection of shifts. In the periodic case, it's immediate. The period is getting smaller and smaller, and as soon as we have shift with one period, we obtain the same coefficient. And it's well known that in the periodic case, we have a nice homogenization result, and homogenized operator is operator with constant coefficients. Similar arguments can be used in quasi-periodic case and in almost periodic case. Also, we have a certain invariance with respect to the shift. And what about random coefficients? In which sense should we understand this invariance with respect to the shift? Of course, if we have a realization of a random function, it cannot be invariant with respect to the shift. There is no periodicity or quasi-periodicity. But what we can condition, what kind of condition can we impose? This condition is invariance with of the law of the distribution of our coefficient with respect to the shift. So we do not claim that this field is random field is invariant with respect to any shift, but its distribution, its law, is invariant. And these coefficients are called, if this condition is satisfied, these coefficients called stationary or statistically homogeneous. So for random coefficients which are stationary, we also expect that homogenization result holds, and I'm going to, in the first part of my course, I'm going to justify this, to prove that indeed for elliptic operators of divergent form with statistically homogeneous random coefficients, the homogenization result takes place. So first of all, let me introduce this stochastic framework. So we have a standard probability space, omega f p is a standard probability space. What does it mean? Omega is an arbitrary set. This F calligraphic is the sigma algebra of its subsets, and P is the sigma additive positive measure, such that P of omega is equal to 1. That's the standard definition of a probability space. And then we have a matrix field A of x omega. And we say that this field is it's measurable with respect to x and omega in the sense that is measurable. This function A of x omega is measurable on Rd times omega. So x belongs to Rd. Omega is a probabilistic parameter. It's for fixed omega, it's a realization of our random field. And we assume that it's measurable with respect to the product sigma algebra. Lebesgue or Borel sigma algebra in with respect to the product sigma algebra, Borel sigma algebra in Rd, and sigma algebra F, which is given in the probabilistic space. So, with respect to, and what does it mean that this field is stationary? The classical definition of stationarity or statistical homogeneity, I say sometimes stationarity, sometimes statistically homogeneous, it's the same thing. In fact, traditionally, in one-dimensional case, people say stationary field. In multi-dimensional case, people say statistically homogeneous field. But in fact, the definition is the same. So definition, A of x omega is statistically homogeneous if for any collection of points from Rd and any vector y also from Rd, the law of A of x1 plus y omega, A of x2 plus y omega, and so on, A of xn plus y omega, is the same as the law of A of x1 omega, A of x2 omega, and so on, A of xn omega. You see, it means that the shift of arguments for any collection, finite collection of of matrix A, evaluated at point x1, x2, and so on xn, for any such collection, the shift with a fixed vector y doesn't change the law. So that's the translation invariance I discussed with you some minutes ago. But it turns out that it's quite uncomfortable to work with this definition of stationarity. So now we're going to introduce the so-called dynamical system in the space omega. So our next topic is dynamical system in omega. So by definition, the dynamical system is a collection of measurable maps Tx from omega to omega, measurable, and such that the following three conditions are satisfied. X is a parameter. X, when I write X or Y, it will be always element of Rd. So the following condition, three conditions should be satisfied. First, it should be a group. So Tx plus Y is equal to the composition Tx and Ty. And T0 is the identical map. The second condition, Tx preserves measure P, which means that for any set A from F, we have P of Txa is equal to P of A. And the third condition, which is also very important, the map T is measurable as a map from Rd times omega to omega with respect to the pair of arguments. So as before, in Rd, we use the Borel sigma algebra. So it's measurable as a map from Rd times omega equipped with the product sigma algebra, Borel sigma algebra in Rd, and sigma algebra F in our probability space. And it maps this product Rd and omega into omega. So if these three conditions are fulfilled, we say that the group Tx is a dynamical system. Why this notion is important? Because let's consider, because it's a way to introduce the stationary field in more convenient case. Convenient, when I say convenient, I mean that we want to use some functional analysis theorem, and this is getting easier if we change a little bit the framework, and then instead of classical definition of stationarity, we use the following one. We say that the A of x omega is stationary, is statistically homogeneous, if there exists a random field, a matrix valued field A of omega, function of omega only, there is no x here, such that A of x omega is equal to A tilde of T x omega. So dependence on x is coming through the action of the group Tx. So we just apply the map Tx to the argument omega, and this gives us the dependence on x. And now, of course, you can ask me, why should we change the definition? Are they equivalent or not? They are almost equivalent in the following sense. It's easy to check, and it's an exercise for the students. To check that the field A of x omega defined through this A tilde, that this field is statistically homogeneous in the sense of the previous definition, of the first definition. It's an easy exercise. You should just use the Fubini Theorem, and you will see that, and the property of the group Tx, and you will see immediately that indeed the random matrix field defined by this formula is indeed statistically homogeneous. But what about the converse statement? Converse statement, in some sense, is also valid. If we assume that the field A is statistically continuous, and in all the application it is the case. So if we let me write down the converse statement. Exercise. I didn't finish the exercise. This field is statistically homogeneous. The converse statement is, in some sense, also valid. Namely, if A of x omega is stochastically continuous, then there is probably a larger probability space, and there is a group, then there exists a larger probability space, and a dynamical system Tx on this probability space such that A of x omega, and of course the matrix A tilde, the matrix valued function in this probability space, then that A of x omega can be represented as A tilde of Tx omega. And due to this result was justified for the first time by Dub, and now you can find this result in any textbook on probability theory. And due to this result, we can assume from the very beginning that our stationary statistically homogeneous field is defined in terms of some dynamical system and random field A tilde of omega. Well, now we also need the notion of ergodicity. Well, we say that the dynamical system Tx is ergodic if for any set A from the sigma algebra F such that Txa is equal to A, we have P of A is equal to 0 or P of A is equal to 1. So any set which is invariant with respect to the group Tx for all x from Rd has measure 0 or 1. So up to the set of 0 measure, either it's empty set or the whole set omega. And from now on, the result I am going to present, that is the result on stochastic homogenization, is valid for any field, not necessarily ergodic, but the formulation of the result is much easier in the ergodic case. So from now on, we will assume that our group Tx is ergodic. So from now on, we assume that Tx is ergodic. Now in the space L2 of, we can introduce the dual group of unitary operators. We introduce the unitary operator Ux omega defined by U of Tx omega for any U from L2 of omega. So we take the function from L2 and we define the operator U as the operator as the shift by shifting the argument with the group Tx. And it's another exercise to check that the family Ux is a group of unitary operators. So exercise Ux is a group of unitary operators in L2 of omega. This is quite straightforward. Again, you just use the property of the group Tx and well, basically that's it. Also Fubini Theorem and the fact that Tx preserves the measure. Now we want to show, we're going to use the Stone theorem, and in order to apply the Stone theorem, we want to know that the group Ex is strongly continuous in L2. So it's a lemma. the group UX is strongly continuous in L2 of omega. Well, proof. Let us prove this. Let's first assume that f, function f, is an element of L infinity of omega. Then we have the norm of UXF minus f square in the L2 of omega. Since it's a group, of course, it's sufficient to prove continuity at 0. So we have that this is equal to integral. By definition of L2 norm, it's equal to the f of t x omega minus f of omega square dp. And now we do the following trick. We can write that this is equal to integral of over omega, integral over q1, f of t x plus y omega minus f of t y omega square dy and then dp, where q1 is the unit cube. Unit cube centered at the origin. So it's minus 1/2 plus 1/2 to power d. Let me write it explicitly. Q1 is minus 1/2 to power d. Here I use the fact that the group Tx preserves the measure p. So by the Fubini theorem, for each y, what is written here, we can remove y and the integral will be the same in p. So I use the property of the group Ty and the Fubini theorem. Well, and now I keep this formula and continue here. For any realization, by the continuity of the shift in L2, we have, in fact, for any function g, we know that the integral of, in particular for x, t x plus y omega minus f of t y omega dy square. This tends to 0 as x goes to 0 for almost all omega, and this is just continuity of L2 function with respect to the shift. And then we use Lebesgue dominated convergence theorem. Look, for almost all omega, this integral, interior integral, goes to 0. And since function f is from L infinity, you remember, we can use Lebesgue dominated convergence theorem, and we can conclude that the norm UXF minus f square L2 of omega tends to 0 as x goes to 0. And that's the desired strong continuity of the group UX in the space L2 of omega. Now, yeah, and this was proved for function from L infinity, and then since UX is a group of unitary operators, then we can just use standard density argument to conclude that the statement also holds for any function from L2. Well, now in the same way, we can show that using Fubini theorem, we can also justify the following statement. If f belongs to LQ of omega, for some q greater or equal than 1, of course, then almost surely f of tx omega almost surely means that we fix omega and consider this function as function of x. And by the Fubini theorem, for almost all omega, this function a measurable function of x, and moreover, this function are elements of LQ log of Rg. Of course, we cannot claim that they belong to LQ of the whole Rg only locally. And if Fk converge to F in LQ of omega, then almost surely, which means for almost all omega, for a subsequence, Fk of T omega converge to F of I put dot here to emphasize that we fix omega, and this function is a function of is treated as a function of x. Well, let me show to make you familiar with this technique. Let me also give you a proof of this lemma. So since we are going to show that, and also in, I forgot to write that, of course, it's NLQ log of RD. For any, let's say, ball B of arbitrary radius, but fixed, we have 0 is equal to the limit k goes to infinity, the volume of B times integral of omega fk of omega minus f of omega to power q dp. So far, just the consequences of the fact that we have convergence of k of fk to f in LQ, just the definition of this convergence. The factor b doesn't change anything. This is a constant. It doesn't depend on k. And this is equal to the limit k goes to infinity, double integral omega b fk of tx omega minus f of tx omega, then dp dx. Well, here again, I use the fact that Tx preserves the measure and the Fubini theorem. So this part is straightforward. The only yes, and since we integrate this over B, this volume of B was consumed by this integration. Then this is equal to, I just change the order of integration. K goes to infinity, integral over B, integral over omega, f k of t x omega minus f of t x omega. I forgot to power q here. I should not forget it here. dx dp. Well, and you see now it is straightforward that for a subsequence, the interior integral almost surely goes to 0. Because from a sequence which converge to 0 in LQ, you remember that this integral, this limit is equal to 0. Since the double integral goes to 0, then interior part goes to 0 in L1, and for a subsequence, it goes to 0 almost surely. And that's what we need. For a subsequence, the interior integral almost surely converges to 0. And the lemma is proved. Well, and we will widely use the Bergov Ergodic theorem. So in order to formulate it, I first give the following definition, which will be also useful for us. We say that a function f from L1 of Rd has a mean value and we will call it m of f if for any bounded Borel set B from Rd, we have the limit s goes to infinity 1 over s to power d integral over sb, the homothetic dilatation of the set B, f of x dx, which is of course is equal the limit epsilon goes to 0 integral over b f of x over epsilon dx, and this is equal to volume of b times this constant m of f. So we say that this f from L1 has a mean value, which is called m of f, if this limit relation holds for any bounded Borel set B. In this definition, we do not claim that B has a positive measure. Usually, people divide by the volume of B, but then we should impose a condition that the volume of B is positive. Here, we don't need this condition if we formulate the mean value property in this form. And now we can formulate the Bergov ergodic theorem. Which is one of the main tools in our analysis. For any f from L 1 of omega, almost all realizations of f have a mean value moreover. In the ergodic case, m f of t omega is equal just to the expectation of f. So this mean value doesn't depend on the realization, and just it is equal to the expectation of the random variable f. Bergov theorem also holds for non-ergodic case, but we decided that we today dwell only on the ergodic case, so I stop here. Well, and now a simple and very important corollary of the Bergov ergodic theorem. Which states that if f belongs to LQ of omega, then almost surely f of t over epsilon omega, the realizations of f with the scaled argument converges to a constant equal to the expectation of f locally, weakly in LQ log of RD. Which means that for any fixed bounded domain in RD, the sequence f of tx over epsilon omega converges to the constant equal to expectation of f in LQ of this domain weakly. Of course, this is as epsilon tends to 0. Well, now let me give you some examples. No, before giving examples, I think I want to introduce the random operators. So we introduce the random operators with a random coefficient, epsilon, which is divergence, u, divergence, a of tx over epsilon omega, gradient u. This epsilon is defined, in fact, can be defined in the whole space RD, but since we're going to study the classical homogenization problem, we will consider it in some bounded domain. So now, given a bounded domain, let's say smooth Lipschitz, bounded domain Q, we consider a family of problems. A epsilon u is equal to f in Q, and Dirichlet boundary, homogeneous Dirichlet boundary condition u of dq is equal to 0. And under natural ellipticity condition, which we assume to be satisfied, of course, we will have for each epsilon, we will have a nice solution with nice estimate, a priori estimates, and we would like to know what happens to this family of solutions as epsilon goes to 0. So what do we assume? We assume that A of omega assumptions. A of omega is the matrix field which satisfies the condition. So uniform ellipticity condition. Just for simplicity, we assume that the matrix A is symmetric. In fact, it's not necessary, but since I'm going to show you the method of dealing with stochastic coefficient, random coefficients, I prefer to simplify the framework as much as possible. So we will assume that the matrix field A is symmetric. In fact, it's not necessary. Well, and all other notion were already introduced. We assume that it is stationary in the sense that there is a dynamical system, and we assume that that this field is ergodic, so ergodicity. Let me repeat it one more time. So, okay, my time is over. So I think I just formulate the main result which we are going to prove. Theorem. Main homogenization theorem. There exists a constant symmetric positive definite matrix A, let's call it A home, such that for any f from L2 of Q, the solution U epsilon of problem, let me mark it with star here, of problem star converges in L2 of Q to the solution of the following problem. Divergence A home gradient U is equal to F, U at dq is equal to 0. Since A home is positive definite, this limit function is defined uniquely. And what is important, that A home is constant matrix both with respect to x variable and with respect to omega. So its limit is deterministic and the matrix is constant. So tomorrow I will show you how to the method of proving this theorem, the argument which will lead to this result, and also we will show how the corrector can be constructed in the random framework. Well, I think I stop here.
Okay, thank you, Professor Andrey. So, any questions? You can type it in chat box. Right now, I don't see any questions, but you are. Or maybe Andrey can come on. Video can switch on so you can see. Yeah, now we have got one question. Can we extend the method to sigma finite measure spaces? Hello, Professor?
Yes, sigma finite measure spaces. I'm not sure if I understand. If I understood the question. In which sense? Maybe you can unmute the person
Yeah,
who is asking that.
maybe Vivek can unmute or can give the permission. Or maybe the next question will go by that time. Can you give some examples of statistically homogeneous media?
Yes, sure. There are many examples. Tomorrow I will give you a collection of examples. But typical example, okay, one way to construct an example is to use periodic structure and then take at each period, let's say we have some constant matrix plus, let me write it down. We have a constant field, and then, okay, I write it in one dimension, but it can be done in the same way in any dimension. And around each point, we draw a function, which is the same for each integer point. And then we change the location of the center of this point randomly. We take IID, identically distributed independent random variables, and then we shift the central point of this at random. So instead of this, let me draw it in another color. So we have here we have this one. This one will be somewhere here. This one will be somewhere here.
Yeah, Professor Mikhail wants to make a comment. He is unmuted now. Maybe Professor Mikhail?
Andrey, I just wanted to make a short comment, just probably for the listeners of the talk.
Very good, sir. Welcome.
When you say that when you take a function f from LQ of omega and you take its physical realization f tx omega, you say we cannot claim that it is in LQ in the whole space. I just wanted to say that not only we cannot claim this, but it's not true. So as soon as function is not zero, its integral in the whole space diverges, right? So it's never in L.
Sure. In fact, thank you for this comment. That's what I meant, in fact. By Bergov theorem, just
Yes.
almost all realization, it will be infinity, the norm and the whole.
Yeah.
Absolutely. Yeah, thank you.
Thank you, BK. It's very nice. So we have one more question from Elchich. What if we drop the assumption on ergodicity and assume only statistically invariance?
Yes, the results which we discussed remain valid, but the limit, the effective matrix will be independent of x. It will be constant in x, but it will be random. Dependence on omega will be kept. And the only thing which, the technique which I'm going to present will work, but it gives us the random effective matrix, which is just measurable with respect to the so-called invariant sigma algebra. If there is interest to this question, maybe I will give tomorrow or day after tomorrow, I will give some comments about it. What happens in non-ergodic case, but in the non-ergodic case, the result holds. The only difference that we cannot claim anymore that the effective matrix is deterministic. It is not in general.
Thank you. Thank you, Professor Andrey. Any more questions? I think no more questions today. So the thematic lectures of today are over. So we'll more or less close the session, but there's an informal meeting which we said. So those who are, today's informal meeting is just to get to know the participants. So get to know each other. When you are an offline meeting, we will meet everybody and talk to them. Where are they? So it's there's no agenda in the meeting. So those who are interested can join the meeting. This will start at after half an hour at 6 p.m. Indian time, IST. Okay. Otherwise, the main program of today is over. Okay, thank you all. So we will, those who are interested can come the meeting. We'll just get to know each other. Thank you. Thank you, Andrey, for the nice lecture.